Hi everyone. Today we would like to present about our mini project proposal, which is called the Smart Retail Guardian Perishable Goods Monitor. My name is Samuel Raja, and my friends MOVINDKUMAR, Mageswaran, and LUQMAN will help present the other slides. My friend LUQMAN is going to give the a short, brief introduction about the our mini project.
The retail industry is increasingly adopting smart technology to manage store environments efficiently. The Smart Retail Guardians applies this concept by automating the care of temperature-sensitive inventory. The scope of this project is to build a connected system using the ESP32 microcontroller that continuously detects changes in temperature and shelf occupancy. It is designed to automatically trigger a cooling fan when specific conditions are met, and simultaneously transmit live data to a mobile app, giving store managers real-time visibility and control over their stock.
This project contains three problem statements. First of it is lack of real-time visibility and delayed response. Store managers currently lack immediate data-driven insight into shelf-level environmental conditions. This results in a delayed reactive response to temperature anomalies or potential cooling system malfunctions, often after the damage is already done. Next, overcrowded or fully stacked shelves restrict airflow. Fluctuations in ambient temperature, often caused by poor air circulation due to overstocking or cooling system failure, can push items out of storage limits, resulting in spoilage, financial losses for the retailer, and increased environmental impact. Finally, absence of automated response to abnormal temperature conditions. Retailers often rely on manual inspection or periodic checks to identify temperature-related issues. However, by the time the staff notices a problem, the goods may be at risk. For the objective, first one will be to design and implement an IoT-based real-time monitoring system. Second will be to determine shelf stocking status and analyze airflow obstruction. Finally, to automatically activate auxiliary cooling mechanisms when needed.
For the hardware design, the first one is that the inputs are the DHT22 sensor, which is the temperature and humidity sensor. This sensor plays an important role as it measures the ambient air temperature and humidity to detect whether if surrounding temperature is either high or low, or is it cool or hot. So for example, if you for leafy vegetables, you need to have it needs to be in a certain temperature to avoid it from getting spoilage. So we'll use that sensor to detect and check. As for the ultrasonic sensor, it is to check and see whether there more stock or is there less stock. So the more heavy it is means there's already a lot of stock. But if it keeps going low and low, it'll inform the user, I mean the seller, that we need to put in more stock. As for the outputs, we have four, which is the relay, the DC fan, OLED display, and the mobile app. So for the relay, we are using for the fan. So for example, if it reaches a certain threshold, like if it's too high of a temperature, the fan will turn on. If it's too low of a temperature, the fan will turn off. As for the DC fan, we recommended 12 volt because 12 volt is the default settings for the fan, and also it produces the correct RPM to cool down the vegetables. As for the OLED display is meant as an emergency. For example, if the mobile app goes down, or like something like the internet were to go down or something, so we can use the OLED display to display all the messages and notifications to the seller. As for the mobile app, yes, it is that is our main target, where we actually created a mobile app to check and see, like have a dashboard to show and see whether the temperature is high or low, or maybe also to check and see whether there's stock or not enough stock. Powering the whole system is going to be a MD102 power module. This one is to regulate the raw input voltage from a 9 volt battery or maybe a 12 volt adapter down to a safe 5 volt and 3.3 volt for the ESP32 and also for the sensors. Next. Okay, so this is our block diagram. So if you can see, we only have two outputs and four outputs, and also the power module to power up the whole ESP32. As I mentioned, this we are going to use Flutter to develop the app, and as well from the app with the user will receive notifications, and also the OLED display will play as a backup plan.
So as for the software design, we have two software components in this IoT project, which is embedded software and also web-based monitoring. So the next slide. So for the first and main component in this is the embedded software running inside the ESP32. This is the firmware that we developed using Arduino IDE application. It controls all the sensors and hardware in the real time using ESP32 microcontroller. The reason we're using this software is because Arduino IDE is a lightweight, simple, and provides a ready-made libraries for the sensors that we are using, such as DHT sensor, ultrasonic sensor, and it also contains a ready-made library for the Wi-Fi module and also a relay control. This allows the ESP32 to process data quickly and react immediately to the temperature rises and respond towards the IoT updates. In our system, the firmware continuously reads temperature, humidity, and shelf occupancy. Based on the threshold logic, it decides whether to turn the cooling fan off or on. So basically, this embedded software acts as a brain of the entire system. The next slide. So the second part is web-based monitoring, which developed using a Flutter. So this dashboard is used by the store manager to monitor the system in real time. So the software is basically developed using a Flutter application. So we choose a Flutter because it's a cross platform where the same dashboard can be used smoothly in laptops and also tablets and smartphones. The Flutter also supports fast UI development, and it's a real-time. It's better for the real-time communication with Firebase or MQTT, which is important for real-time IoT data updates. And then throughout the dashboard, the manager can see the temperature, humidity, and shelf occupancy instantly. If the temperature goes above the safe limit, the dashboard will show an alert system to the admin who is monitoring. All the data is stored for the feature analysis, making the dashboard as the main interface for the monitoring and controlling the whole system. So as we can see, here's an image that how IoT our microcontroller will connect to the cloud and will update the real-time data reading to the website. So that's all for the software design.
In conclusion, this project successfully demonstrates the design and implementation of the Smart Retail Guardian, an IoT-based system that effectively addresses the critical challenge of perishability management in the retail sector. By integrating the ESP32 microcontroller with a robust sensor array, the system achieves its primary goal of autonomous environmental regulation, detecting thermal anomalies, and triggering immediate corrective cooling without human intervention. Furthermore, the successful deployment of a Flutter-based mobile dashboard via the MQTT protocol proves that real-time, low-latency telemetry is achievable with cost-effective off-the-shelf components. Ultimately, this prototype validates the Retail 4.0 solution need not be prohibitively expensive, offering a scalable model for reducing food waste and improving operational efficiency in smart buildings.
Thank you everyone for listening to our presentation.